I'm going to talk about transition we are doing at the University of Poitiers in a master's degree. I teach digital communication, and for quite several years, and I want to go to something that's really working and well, not only stay at the simulation level. So this project is going to show you all the problems I've had to go to this step. And as you can see, you've got a DPLL with the famous timing error detector shown here. So I'm going to talk about that, of course. So the introduction and motivation first, and then I'll talk about the QPSK modem with the main building blocks. Then I'll show a fully digital QPSK synchronizer, and then I expect that everything is going to work with the Pluto this time. So I'll show the result on the radio going on RF. And then I'll finish with a conclusion. Okay, so motivation. So yeah, I'm an old man, 59 years old, and I've been teaching digital communications for more than 15 years at undergraduate and graduate levels. I've used extensively MATLAB and Simulink and the communications toolbox to show the main aspects of digital communication. I know this tool pretty well. It's not free, but it's really interesting for the students. They even if they don't know the tool, they get accustomed to the tool quite rapidly. The University of Poitiers has got a license for all the students, so for us it's not a problem. But it's a proprietary software, and that's my problem, because I've started to go away from Windows and all paid software. So that's why I'm really interested in GNU Radio, and well, we'll see that it's a good alternative to this thing. With one thing you have to have in mind is that it's not designed for simulation. GNU Radio, for me, is not designed for simulation. So that's probably the main difference between the Simulink and the communication toolbox and GNU Radio. So, is it going now? Yeah. So up to this year, in the second year of the IoT master's degree, we've got two disjoint topics really teach in this digital communication course. So all the basics of digital communication plus error correcting codes. This is my part. And my colleague deals with the hardware aspects, especially the linearity in RF amplifiers. What we want to do is to make connection between these two topics. Both of us use MATLAB and Simulink for that. And in fact, I took this opportunity this year because my colleague discovered the power of GNU Radio in a digital pre-distortion research project using GNU Radio. So it was the right time. So we've decided together to give some more coherence to the course. So by replacing, I expect next year, totally MATLAB Simulink by GNU Radio. As I said, at last I have to say that because I don't want to have troubles with Jean-Michel. And also, this is something that I quite like, is to give more space to implementation with the design, in that case, of a real-world QPSK modem. So GNU Radio plus hardware. We've got plenty of Pluto, Adam Pluto at the University of Poitiers. And we will add, of course, the linearized power amplifier as well. So this presentation is going to be about the difficulties, not about PCs and graphic cards configuration, but the difficulties you're going to face when you go from simulation to implementation. Since it's the topic of these 2 days, I will focus mainly on synchronization aspects. And well, anyway, no choice, because no synchronization means no real-world implementation anyway. So the QPSK modem, starting from my friend Shannon. You all remember about, about that. Well, it's not for the sampling theorem, but for all the theorem about communication, and especially digital communication. So source encoding, encryption, because Shannon is also known for that, and Shannon encoding. So you see that with source encoding, we reduce the bandwidth, and with channel encoding, we do exactly the reverse, but we adapt to the channel. And of course, you've got the blocks at the receiver side. We start with bits, and we receive bits. So if you get more precise, then you've got here the digital modulator and demodulator and the discrete channel. When you start by introducing the waveform transform with pulse shaping, spectral transform if you adapt, if you change the frequency, if you adapt to the channel. And I'm going to be more precise to show my modem that you can see here, the way it's placed in this slide. So bits to bits, and of course, what I'm going to be interested in is about the modem part for the transmitter and the receiver. So more specifically, you came with this block diagram where you find everything you need to build a fully functional QPSK modem. This comes from slides from Fred Harris, who is really a guru in this domain, and he's you can find some of these slides on the internet, and they are really good. It's someone who's worked also with Michael Rice, with another researcher that has brought quite a lot to this domain. So we'll find the modulator. So I'm talking about IQ transmission. So in fact, QPSK, so in phase and quadrature channels. Of course, the pulse shaping that you need to go to the time domain. Then you go to upsample, go to your carrier. Here you've got a digital to analog converter, and then again, but this can be reduced today with frequency changing stages up to the power amplifier. Then the receiver side, you've got, you see here the carrier PLL. So you've got to recover the carrier. So is the thing about Thomas talked to you about phase. When you've got frequency and phase, that's going to I want to say the frequency. When you've got not exactly the same frequency at the transmission and the receiver side, you will have these problems, and also the problem of the timing that you have to recover, because you're not exactly aligned with the symbols that you are transmitting. So this has to be in your system if you want it to work. So there's the first thing I'm talking about. So the main building blocks is the pulse shaping and the match filtering. I suppose that most of you know the important thing of match filtering for a system like that. So you limit the bandwidth. That's the first goal. Then, of course, you maximize the SNR at the decision points, and also you reduce intersymbol interference at the receiver. We use the well-known root race cosine pulse, so one at the transmitter and another one to the receiver, which is going to be the match filter to the first one at the transmitter. So at the end, you've got a race cosine response for all the chain. So this respects the Nyquist ISE criterion. That's for that. In practice with GNU Radio, I had some problems also with GNU Radio and the way the filters are designed and documentation not very clear about that. Come back to this afterward. In fact, the important parameters, first thing is the upsampling factor in samples. If practically you would go from 4 to 16. Okay, if you look at the implementation in GNU Radio, it implements polyphase filter by default, and it goes up to at the end 2,500 coefficients. So that's, for me, it's too much. If you for a PC, a classical PC, it's okay, but if you want to go to a embedded system, it's too much. So there's another parameter called the filter span. So the filter span is simply because your root race cosine pulse has got is defined between minus infinite to plus infinite. So you have to limit to a number of symbols. So practically it's around 8 to 12. Okay. So and the last parameter that is important is the roll-off factor. It's the excess bandwidth if you could realize this filter with a cardinal sign, which is not realizable physically. So it's generally between 0.25 and 0.6. Another thing you have to be careful about is, okay, you want to reduce the bandwidth, but if you go too low with this roll-off factor, you'll have problem with synchronization, because studies have shown that ideally you should have a value of 0.35 over 0.35. It has to be greater than that if you don't want to have problems with the synchronization. So you see, I tried with 3 software. The reference for me was MATLAB, of course, because I know these functions and I know exactly how they work. You've got also Octave and the GNU Radio FIR-DS with the root rate cosine. And so I just checked the realization of my filter using this software. And what you've got here shown is simply the filter that are calculated by GNU Radio with the parameters shown here. So alpha is 0.35, an SPS of 16, and a span of 11. So you see that on the right that the frequency occupancy is of course limited to your symbol rate. I'll come to this just afterward. The larger the span you take, and the lower you go with the spectral regrowth that you can see on the figure. So it's a compromise depending on your channel, transmission channel. So another question is how many samples per symbol? So N is equal to TS divided by T, with TS the sample rate and T the sample rate. In practice, we take between 4 and 16 samples. Another important thing when you go for implementation, it seems to be obvious, because on devices like this one, you've got an automatic gain controller on the electronics, but it's not enough. You have also to perform an AGC at baseband. So you have to be careful about that when you design your loops for symbol synchronization. They work with an average level, and if you don't reach this average level, it's just not gonna work. I'll show this afterwards. So to start with, what do you do? In fact, you start with unit energy. So it means that you take your QPSK constellation and you take 1 joule for ES, which is the symbol energy. So to get the amplitude, you apply this formula here, and it gives you an amplitude of 0.707, the square root of 2. Okay, so the receiver functions are designed to handle this value, which has to remain constant. So the AGC is also a block that you will need. So it's again a loop. R is simply the reference. So you set it to 1 volt, for example, and alpha is a coefficient so that you adapt to have, well, for the reaction of your loop. If C, we had another constant here, if C small, you've got a long transient, and if C is large, you're going to have a short transient. So this block you find in GNU Radio is the AGC2, which works quite well, a bit more precise. You can really adapt the attack rate and the decay rate of your system. So now, some more loops, talking about loops all the time. In fact, we need 2 more loops, the carrier loop, carrier synchronization loop, and the timing loop. So these are PLLs, phase-locked loops. And for the carrier and phase recovery loop, this is the one represented here for QPSK. Typically, when you haven't got a loop like that to recover the phase, you will see your constellation. In fact, the points are turning around the circle, and you'll see that if you implement this loop, if it's properly designed, you're going to find again your QPSK symbols. Be careful about that. That's another thing that's important. You've got a P divided by 2 phase ambiguity on this system. So it means that even if you look at your constellation and you see that your points are perfectly on, you think, at the right place, you can have a phase ambiguity. So if you don't perform differential encoding, or you use techniques like the unique word technique, you probably won't have the right data. You have to be careful about that. And then the other one is the timing recovery loop. If you've got a constellation that looks like that, it's a problem of timing. Okay, so you need another loop that we're going to detail afterwards. So to be able to design properly these loops, you need to have a minimum of elements about PLLs. So here I've represented the analog PLL, and with all the parameters, classical parameters, it's a second order function with zeta and omega n, the natural frequency. The parameter that's going to be very important for us is the PLA noise bandwidth, and yeah, that's going to be the key element. So now what we want to do is transform this analog PLL to a digital PLL. So the digital PLL is represented here on the left. It gives you the transfer function that you've got on the right. It's called HD. And what we do afterwards is simply apply the Tustin's equation to HA, which was here, and we equate the denominator of the polynomials, and it gives you the relation between theta n, zeta, and the constant, the important constant of the loop, which are Kp, K0, K1, and K2. So Kp is the gain of the phase comparator, K0 is the VCO gain, and K1 and K2 it's for the filter. I'm only talking about second order PLLs. So finally, you've got the right formula that we need to design our loops, and these equations you find them in Rice's book. He's got a chapter on that, and it's really nice the way it's presented. So I tried with again my MATLAB to implement a loop like that, and I generated a sine with not exactly the same frequency the loop was supposed to lock on, and I was able to try with the constant I calculated to see the phase error and to be in lock. So this is done just with a MATLAB program. You can do it in C or what you want. So even an oscillator, you can do it numerically. So that's really nice about that. So now the fully digital synchronizer. So in fact, what you see on the left is what we want to build. So it's we've got the Costa's loop in red, and all the other blocks are the timing synchronization loop. So we want to build that, and the question is, has it something to do with what you see on the right? That is the symbol sync block and the Costa's loop that is just afterwards. So, well, in fact, yes, but that's yeah, the problem is that you have to identify, if you want to understand, in fact, the way it works, you have to understand some of the important blocks that are inside the code of GNU Radio. To be honest, it works pretty fine. So, in fact, I'm not going to talk about the Costa's loop. I'm going to talk only about the symbol sync, because a lot of people ask me for that since this morning. So, so I used Andy Wall's GNU Radio design block, and that was in 2017 for GRCon. So he designed, in fact, something that's almost the same as you can see on the left, just for the timing part. So what do we find in this loop? You've got, in fact, an interpolating resampler. You find something interesting, we talked about that this morning, is the timing error detector. So what's interesting here is that we'll be able to choose the different timing error detectors because he's implemented several TEDs, and also what he's done is code is really well written so that you can also add your own TED if you want to add something new. Okay, nobody has done that since 2017. I don't think so. Okay, so just about the timing synchronizer. In fact, the TED, the timing error detector, plays simply the role of the phase detector of the digital PLL. Okay, this best the way it works best understood with the eye diagram, whose slope can be used to generate a timing error, which is E of k for binary PAM represented here. So what we can see on the left with the eye diagram. So the eye diagram, suppose that everybody knows what an eye diagram is. You just it's a superposition of your symbols, digital symbols at baseband, or over two or more symbol instant, in fact. Okay. Well, yeah, most of the time, yeah. Okay, so in fact, it's a superposition of all your data. So it's difficult to see the transitions from, for example, a -1 to a +1, or well, that's probably the difficulty. But what we can see on the left is that, in fact, the optimum sampling instant for your timing synchronizer is to take the time tau here. That is exactly at the place where the eye is opened at the maximum. Okay. So if you take the time derivative of your A diagram, you got the figure on the left. So in fact, you see that the optimum sampling instant is when you've got zero transition. Okay. So it's interesting to see that we could design a system to calculate the error using the A diagram and also the derivative of the A diagram. So on the right is represented the 4 possibilities you can have when you try to get the optimum sampling instant. So the error is represented, for example, on the upper left one, you've got the error that's positive because you take your sampling instant too early. Okay, so you have to increase your error, and it's in the case you've got as a data A of k that is +1. All the cases are represented here. So what we can see is that for the error signal, we could use, in fact, the expression that's represented here. It's multiplication of the AK, which represents the data, and the derivative of the X, which is, in fact, the A diagram. So, in fact, that's just a representation of the maximum likelihood timing error detector. So now, to go a bit more to practice, what do you have to choose? What do you have to understand to have a TED working? In fact, the characteristics of your TED is described by what is called the S-curve, which is G depending on the error, the time error. Okay, so here you've got an example for this maximum likelihood TED, and you will get, in fact, a gain, if you look at the graph on the right, a gain of this timing error detector, which is the KP we saw just before. It's the gain of your TED that you have to put into the block and this whole block. So the problem, and this whole gave a MATLAB script to determine by simulation these different KPs, but only for not for RRC pulses. So, in fact, I've calculated all these gains, and it gives you, according to your roll-off factor, it gives you the coefficient you have to put into the block. So this work has been done again in the Rice's book. So now, rapidly, I don't know if I'm okay about the time or okay. The last important thing to know about this timing loop is that you are not synchronized with your ADC clock. You've got a new time domain that you try to synchronize with the symbol time. So to do that, when you're not exactly at the right place to at the center of the eye at the maximum opening, what you have to do is to interpolate and find a value that's not existing in the data, but you can reconstruct this data with the samples that you will get. Okay, so all the elements are represented here. You will have the slides for that. I need at least 20 minutes more to explain that because it's a bit complicated. So we need to have a system that is going to fabricate what are called interpolants between the samples, so that your system is going to be locked, in fact. In fact, conceptually, how are we going to do that? An interpolator can be seen as a filter. So if you take direct impulses from the samples that you've got at the output of the DAC, if you pass them inside a filter, you will get your interpolant. So we can use a digital filter to as an interpolator, in fact. And that's the key idea for these systems, and also the system that's been designed by Andy Wall. So we've got the choice between FIR piecewise polynomial filter or implementations possible in Andy Wall's block. You can use a polyphase filter bank to get your interpolant. You massively upsample the input of your match filter, then you sample the match filter output at an appropriately chosen sample offset, so to get your interpolant. Okay. So here is what we do if you take the first possibility, not the polyphase filter bank. Just have to find, it's a French mathematician called Lagrange who has answered to that. You know a polynomial, and for this polynomial, you want to determine the coefficient of this polynomial, knowing the points where it has got to go. So you choose the points and the order of the polynomial, and it's going to give you the coefficient of the polynomial that approximates best your function. So that's what it's going to do. And to do that, we are going to design, in fact, our filter using a method called the Faro method. It's called a Faro filter. And this filter is going to be your interpolator. At the end, it's something for a parabolic interpolator. At the end is what you get. That's for one branch, I, the I branch, and the Q branch is exactly the same. So that's quite fun, because this system, you've got, in fact, the time difference you have to adapt that comes from the error, and you see that the pulse that you enter the system, according to mu of k, it's delayed by a certain amount according to the error your TED is measuring. And that's really, really efficient and can be implemented digitally. the last tricky thing is to add modulo 1 counter to, in fact, determine the base point indexes and also this computation of this mu of k that can trigger the Faro filter. As you can see, it's quite a lot of things, a lot of complicated things. So I come to the demonstration, fingers crossed about the fact that's going to work. So I've taken the Andy's block, symbol sync block, and as you can see, you've got different parameters that you have to set. First thing that you can see is you can choose your timing error detector. So you've got some of them in the list. For example, the maximum likelihood, we've got it. And the possibility to choose an interpolating resampler, also, you've got different possibilities. So my demonstration is about a system using a Nadal Pluto, something quite simple. So I've got the one part of the Pluto, it's the TX, and the second part is the RX, and it's done by a radio. Okay, it's not a loop back. So I've got on the same flow graph the transmitter, so with the block constellation modulator, which works pretty well, and it's Marcus, this block that uses 2,500 coefficients to calculate the filter, the RRC filter, in fact. Again, should be all right. Yes. It's exactly what I wanted to show. So, constellation modulator, 0.35 for the excess bandwidth. Okay, 200K as a data rate. Okay, so my Pluto, and then the receiver. So the receiver is a Pluto source. You see that I've got a low pass filter to eliminate a bit of noise, and my AGC2, which is also present here. And then I'll go to my symbol sync block and this Costas loop. So let's go. Yeah, the other screen is just here. Okay. So normally 200K means multiplied by 135. So it's 270 kilohertz in span. So that's okay. The first constellation you see is the one you get at the receiver without synchronization. Okay. So the Pluto and the oscillator of the Pluto works pretty well, because here I've just added a difference in frequency. You see that you're even a small phase shift. No, I'm adding a frequency difference between the transmitter and the receiver, and you see that the constellation is starting to. And if I go with more than that, you see that the loop works pretty well anyway. Can go. Okay. So the parameters of my system here. So that's after timing recovery, and that's after phase recovery. So the parameters here, I use a TED gain here I use the zero crossing TED, and this TED needs a coefficient of 2.7. So it works pretty well with 2.7. You have to be careful about the loop bandwidth. If you take a small loop bandwidth, it's going to lock rapidly and it's going to be quite efficient. But if you increase for example, the frequency difference between the transmitter and the receiver, you will have to increase your loop bandwidth. Otherwise, you'll lose the lock. So, and the filter, that's another problem also. You see this filter. So I've designed the filter here. If you don't take the right coefficient, the amplitude coefficient of the filter, which is used here inside the CMOL sync, again, you'll see that you'll lose the lock as well. So that's quite efficient. So the next thing I'd like to do now is to have something more realistic. I mean, taking an image at the transmission side and get the image at the other side. So, of course, I'll get the data okay, but I'll have some treatments behind GNU Radio using Python to build a system like that. The ideal, what I did with MATLAB and Simulink, the students took an image, they transmitted the image, and they had the reception of the image, and they could see, for example, that JPEG images are really sensitive to noise, whereas uncompressed images are not. So doing things like that with a type of manipulation like that is, well, what I would like to do, in fact. I lost a bit of time. So as a conclusion, so going from simulation to implementation adds a lot of complexity. So digital synchronization functions understanding and implementation require a good level in digital signal processing. I don't know about your students, but at the University of Poitiers, it's terrible. They haven't got, well, it's not taught at an undergraduate level. I've just noticed that it's not the students the problems, the teachers in some university. And for GNU Radio, digital signal processing is really important. So the students really request practical implementations. So it's the direction where we have to go, that's for sure. And for this particular purpose, GNU Radio is really, for me, the right tool. Thank you for your attention.